Hello, this is my Lab 3 circuits video report, so let's get started. So for this lab, we used two experiments to understand current and voltage in circuits with resistors and capacitors. Then we measured the electric current and potential differences, and we also found the time constant using experimental values. For the results of this lab, we calculated the resistance of the wire to 0 ohms, the 47 resistor to 48 ohms, the 100 resistor to 102 ohms, and the ammeter to 0 ohms. We found that the time of charging and discharging of the capacitor is quite approximately equal, and the experimental time constant was 5.89 seconds versus the computed time constant of 6 seconds. So some important concepts for this lab is Kirchhoff's voltage and current law, and some concepts with resistors. And we also use the formula at the bottom right to find the time constants. So for experiment 1, we had the system being the circuit and surrounding being everything outside of the circuit. We had two 1.5 volt batteries, two resistors in series, one 47 ohms and the other 100 ohms, and two ammeters. We found that the experimental value came up to 0.02 milliamps, and the actual value of the current was zero point 0.02 milliamps. So continuing off on experiment 1, we found that uh, the battery gains its voltage from the two batteries from A to B, and then it travels all the way to the resistors without change. So from BC 0, nothing changes. And then CD is the first resistor, the 47 ohms one, and it loses negative 0.96 voltage, and then it travels to the next one without losing any voltage, and then goes through the um, 100 ohms resistor and loses around 2.04 voltage. Some source of errors from this is imprecise readings from the ammeter, and here are some calculated resistance from the resistors. So for experiment 2, we had the system being the RC circuit, the surroundings being everything outside. We had a 9-volt battery and a 10 ohms light bulb and a 0.2 F capacitor. And then we did the same thing with a 20 ohms light bulb. So the procedure was to measure the time it takes to charge and then discharge the capacitor, and any source of error is just probably human timing. So continuing on experiment 2, some of the results we found was that the 10 ohms bulb charging came to 16 seconds and discharging came to 15 seconds. And for the 20 ohms bulb, it came to 29 seconds, and the bulb discharging came to 28.5 seconds. So the results, what we can conclude from this is that they were kind of equal in charging and discharging times, and then you can just double the time when doubling the resistance. And so using this experiment, we could have found the change in voltage for 20 seconds, and we found the slope, and the slope was negative 0.1724. And then with that, we could find the experimental RC and the predicted RC, and our experimental came to 5.8 seconds, and the predicted was 6 seconds. So some what ifs. If you charge the capacitor with no resistor into the circuit, how quickly would our ideal model predict the capacitor to reach full charge? And would this prediction happen in real life? Um, in an ideal circuit battery with a battery capacitor but no resistor, the math says that the capacitor would charge instantly in 0 time. That's because the ideal model assumes that there's no resistance to slow down the flow of the current. So an infinite current rushes in and fills the capacitor immediately. But this won't happen in real life because every current has some resistance from the wires, and the battery's internal resistance, and the capacitor itself. Because of this resistance, the capacitor actually charges over a short but finite time, not instantly. Also, if the resistance were truly zero, the current would be infinite, which is impossible. Components would burn, or the battery would be destroyed. Conclusion, the experiment showed that the current and voltage in resistor capacitor circuits follow expected behaviors. The measured resistor values and time constants match closely with theoretical predictions. Charging and discharging times were nearly equal, and small differences were likely due to timing and measurement errors.